So the way resistors work is when you try to push electricity through them, they act as though they are a resistance, okay? They resist electricity flowing through them. The less electricity you flow through them, the less they're going to count. A capacitor, on the other hand, when you first flip it on, has absolutely no resistance there at all. It acts like a short, like it's not there. But as charge starts to build up on the plates of the capacitor, the current that you can push on there starts to decrease and it starts to slow down. And then once a capacitor fills up and no more charge can flow, it acts like it's a total just open, like it's broken, like that's it. It's got infinite resistance. And so what happens here essentially is you have that initial resistor and it kind of slowly lets charge start to build up on the capacitor. And at first that capacitor acts like it's not even there. So any bit of current just goes right through and it's like that, it's like only the resistor is there. Then as charge builds up on it, its resistance starts to go up and starts to climb essentially to infinity, such to the point that the other resistor doesn't even matter anymore because the current gets totally stopped once it fills up. And so that's what's happening here. The resistor slows down and steadies how quickly that capacitor can fill up. And then of course, how big that capacitor is and how much it fills up will help to dictate how much of the voltage it's taking up, because it keeps taking up a higher and higher resistance, which means less voltage across the other one, which means the current is slowing down through them. And we can do this by looking at these kind of exponential decays for filling up a capacitor. And right here, we can get this one. You don't need to go through and do this. You can do this, if you've taken calculus, you can do this just with some little differential equations, but we're not going to go through that. And the charge at time t on a capacitor in this situation is the capacitance times the EMF times the quantity 1 minus our exponential to the negative t, which is our time, over tau, where tau is the resistance times the capacitance that you have in there, RC. It's called the time constant. All right, it's called the time constant because you put different amounts in there, you put different values of RC in there, and it changes what that tau becomes, and it changes how quickly it fills up. And then, of course, C times E, C times epsilon is the final charge that ends up on the capacitor at time t, because charge is capacitance times voltage. Okay? So, very important equation there. This is what it's going to look like as far as the charge on the capacitor goes. It's going to increase and go up, right? And it's eventually going to approach some C times E, capacitance times the voltage of our battery. So notice that it approaches up there and it's going to plateau at the capacitance times the voltage. It's eventually going to act like that resistor is not there, because essentially the resistance of that capacitor goes up to infinity, and so it takes up all the voltage. Remember, if you started on these other problems, the largest resistor takes up the largest chunk of voltage drop, right? So if I have like a 12-volt battery and I put a 1 ohm resistor on there, it's going to take up all 12 volts. It has to, because the whole, all the way around the loop has to be 0. But if I have a 12-volt battery here and I put a 2 ohm resistor and then like a 500 ohm resistor, that 500 one is going to take up the vast majority of the voltage. And a very small voltage drop is going to happen over the 2 ohm one. You can sit there and work it out, but it's going to be much, much smaller on the smaller one. So as that capacitor fills up, as it starts to act more and more like a resistor, because it's getting full, like filling up a water balloon, it gets full. It's harder and harder to push more water into it, right? It starts to slow the current down and it starts taking up more and more of it until we go to the limit that is taking up all the voltage. So if the capacitor gets to be fully charged, it's as though that resistor is not there. The resistor just kind of slows down how quickly it gets charged, how quickly it reaches that. All right, you can look right here. You can see after 1 tau, which is our time constant, we're a little bit over 60% charged. All right, and if you want to find out, I don't think it's on here. If you want to find out how that is, take a look at this right here, this part right here. And we want to basically figure out when we put in RC for tau, right? When we put that in there, what do we end up with? And you'll see that you end up, I think it's like 63.63 or something like that. So it's 63% of the full charge. This part right here would equal 0.63. If you put in 2 RC, it goes up to here where it's like 80 something percent, and then really close to being on, 90 something percent, and then like 99% or 98% as you keep putting in different amounts in here. So you would do, you just have to do that 1 minus epsilon, 1 minus e to the negative t over RC, however many, 1 RC, 2 RC, 3 RC, 4 RC, how many time constant steps you look at. Okay? And so it fills up according to how big the resistance times the capacitance is. That tells you how fast we can fill this up. Here we have the exponential decay. This is the current going through it. Notice how it's very similar to what we had there. We still have that exponential to the negative t over tau, except this time the current exponentially decays. As the capacitor fills up, the current is reduced until it eventually gets to 0 and stops. And again, gets very close to stopping at 4 times the time, 4 times our RC, and over here it's almost full at that. So they're very much crisscrossing like that and doing the opposite of each other. So you can see right off the bat, this is not going to be ohmic, right? This means you're not going to apply Ohm's law to these, because Ohm's law says V equals IR, right? And this is not fitting it. Well, the resistance is changing at least. It's not fitting it in the way we want to mess with. Okay. So the resistance is going up and the current does go down, but we're not going to use it like we do with the resistors. Okay. So next, we need to talk about an ammeter. It's a device we use to measure current. If you can see, it kind of sounds like amps, right? It's an ammeter, it's an amp meter. And then a voltmeter measures voltage. Now, these are done in 2 different ways, and we have a lab starting tomorrow. We're going to do this. But you have to be careful with this, because anything in parallel has the same voltage but different currents. And anything in series has the same current but different voltages. So if I were going to ask you to measure the current, how would you want to hook up your ammeter? In series or in parallel to your circuit? In series, because in series, the current is the same. If you hooked an ammeter up parallel to something, then it's not going to get the current. It's not going to get the current that's going through the other things, right? And then voltage. If I wanted to measure voltage, where should I put it? In series or parallel? Parallel, because voltage is the same in parallel. So you can see here, this is what they would have here. This would be an ammeter. This would be measuring the amount of current going through there. So you want very low resistance in there. You don't want it to reduce the current going through there. It's okay. You don't want it to reduce the current going through there. You just want to measure the amount going through there. Now, that gets to be a little dangerous. In fact, most of the time, pretty much always, you never bother to measure amps. You just don't do it, okay? Because it's easier and a lot safer for your instruments to just measure the voltage and then calculate the current. Because this thing has like 0 resistance there, and you're not absolutely certain already that your current that's going through that is inside the range of what your device can handle, you'll break it and ruin it, okay? In fact, when we do this lab, the lab says to measure it with an ammeter, I'm going to have you just measure voltage and calculate it. That is by far the better practice anyway. Okay? So you always do have to be very careful. But current you measure in series. So this would be telling me the total current going from A to B. And voltage you measure in parallel like this. You hook it up around a certain resistor. So this would tell me the voltage dropped across this resistor. And if I hooked it up across the battery, it'd be the voltage dropped across that battery. Okay? So you hook it up in parallel with what you're trying to find the voltage drop across. And then you can use Ohm's law and calculate what it is. So a voltmeter measures the potential drops between 2 points in a circuit, and therefore it's connected in parallel, because parallel has the same what? Voltage. And series has the same what? Current. That's just conservation of charge. If it's in series, if it has to go through one and go through the other, then they have to be the same, right? We're not magically losing charges in the middle of our circuits. They're not like jumping off or disappearing, okay? It's not like David Copperfield is doing the circuit for us or something. So that's not happening. So we're conserving charge and that happens. Any questions on that? And again, you'll see more of this when we get into the lab. No? All right. That is it for this chapter 21, even though I went ahead and moved back the test. So is there anything from here you'd like me to go back in, do again, or, so here's our three options. I can go back and start some more of this and go through more of this if you want to, if you have questions for me. I can start working on the practice problems, in which case we might not even need that evening review session. We can go through them right now. Or three, I can go ahead and start chapter 22. Probably my favorite chapter. It's magnetism.